Hello, everyone. So I've been working on this dApp with Soroban called Color Glyph. It's a V2 of an application I built a long time ago. We finally have smart contracts, so I'm excited to try and rebuild it on a smart contract protocol. Got lots of cool stuff going on, but we're not really here to talk too much about that. I ran across some really interesting issues using Soroban, trying to really test the limits that we currently have on FutureNet for CPU, memory, different constraints that are on there to try and build a good protocol, exploring different mechanics and methods for handling crazy resource constraints. So, but along the road of working on those things, uncovered some interesting issues and features, both when you're developing a contract and testing a contract, on the dApp front with simulation and submission. So I thought I'd just take a video to kind of walk through what I found. I think some of this may prove to be helpful, as it was for me, just thinking through how you go from thinking about contract development all the way through to contract execution and how it affects the cost of things, both on the metric side or the metering side, and then all the way back, kind of feeding from one side to the other, developing, testing, redeveloping, etc. So in Color Glyph, you've got this grid of pixels, and each one of these pixels is itself its own asset. So you kind of have an asset, an NFT glyph, that is made up of many different color assets. There's different characteristics of these colors, both their color value as well as the miner of the color. So there's an owner when a color is mined, and then that miner gets royalty payments whenever a glyph with one of their mined colors gets sold. So there's a lot of like ownership association, both when you're mining a glyph and selling a glyph. So that all gets pretty complex, and it eventually devolves down into large glyphs and having to maintain state in an efficient way. And ultimately boils down to your glyphs can only be so large because you're just storing you can only store a finite amount of information. And so finding that bound was kind of the journey here that I was on, of how big of a glyph can you actually mint right now, given the constraints on FutureNet, and then trying to push my contract code to make that as large as possible. So anyway, I was going through some tests. I had minted a glyph that was, I think, up to like 20 or 21 pixels wide, a square. So each one of these unique colors and unique locations on the map here, the glyph here, and started hitting resource limits way before I thought I would. So right now, FutureNet, and this is particularly on the CPU side. So CPU on FutureNet right now is 100 million CPU instructions. And I was getting errors right around what I thought was like 17 million, which is nowhere near 100. So I was a bit confused. And so this is kind of where my journey started on doing testing. So how did I know that it was hitting on 17? Well, when you do a simulation for a mint or a transaction with Soroban, you have the simulation endpoint on the RPC that you hit to go and get some like budget constraints to basically generate a transaction that you can then actually submit. So you give it some very basic criteria for the actual operation you want to submit, so the invocation of whatever function for the contract. You send that to the simulation endpoint. It runs a simulation and then sends you back information about, here's what we think you should send back as a budget and the auth and other criteria for the actual submission that can make it for consensus. But the CPU is really low, but I was on my tests, but really high on the simulation. So that was just odd. And you can do these tests inside of your Rust. So over here in my contract code, you can see I've got a test for this glyph, and what I'm trying to do is a mint. So we've got our glyph minting. There's a couple of different things you have to do to be able to get a contract ready to mint. So the client here is what we're working with. That's my contract. We'll initialize it with some parameters. We'll build out a color array. We'll then mine some colors that we then use in a mint. And minting is actually done progressively, where you build a transaction, or you build a glyph slowly over multiple transactions if you're building one that's really large already, to try and avoid some of those resource limitations. And then we do this actual minting with a width. So you'll notice the width was none here. So this is us building a glyph with our colors. And then we actually go and we set, here's what we want the width to be, basically saying, all right, I'm done building it. I'm ready for it to exist on chain as a minted glyph. And this is where I was noticing the issues over on the dApp side of things actually submitting to FutureNet. So if we run this test, I've got a print line here that's going to print out my budget. And this is what I was seeing. So we set our budget to unlimited here just so we don't hit any resource constraints while we're testing. But we can see what was actually used, and it's right around 18 million for a width of 21, which is far below 100 million. And this is where I was starting to hit. I think on FutureNet, you can, like, there's some minor differences between how things happen in tests and how things happen on FutureNet. So I was able to get 22 or 23, I think 22 before it started breaking. But still, it's like it's way below 100 million on this side. So it was just very strange to me. Someone pointed out, though, that my VM instantiation was 0. I was testing on raw Rust code instead of actually testing on a WebAssembly code. So inside of an actual network, virtual machine instantiation happens, where you actually pull in the WASM file, you instantiate it, and then you call it. In my test here, that's not actually happening. It's just calling the raw Rust code. So if we switched and you actually build out your contract, and then you pull that in, now the environment here in the test is going to pull in instantiation. And so we should see that VM instantiation go up. We're going to see our total number go skyrocketing from 18 million to 41 million. And this VM instantiation is consuming a much larger number. So, all right, perfect. Now we're actually testing a lot more along the lines of what FutureNet actually does, which is great. This is still way below 100 million, though. And this is kind of where I was able to get to this point, but it was still breaking, and I'm just very confused. But it turns out that currently the simulation endpoint is capped at 40 million, while the actual network is at 100 million. So that's a bit of a discrepancy in Preview 10 right now that will get resolved, where these things are all the same. But it led me down an interesting path of figuring out, well, could I do simulation or could I bypass simulation? Like, simulation almost feels like magic, right? Where it's building out a transaction for you, giving you all these criteria. Is it possible to build a Soroban transaction without running simulation? Just like for now, I'd like to keep testing my contracts and not be blocked on this 40 million issue. So I'm going to go over to this code real quick. There was another really interesting one that someone had mentioned, or maybe I just discovered it, where I wasn't optimizing my contract code. So you can actually, this Soroban CLI, Soroban contract help, has an optimize method where you can take in a WASM file and optimize it. And so if I do that here, I think it's .optimized. And then I rerun this test. So this is an optimized contract code. If I rerun this test, we were at 41 million before. Now we're back below at 37 million. So I was actually, with optimization, able to get myself even higher, better numbers. So I would highly suggest everybody's, optimize your code. It'll reduce quite a significant number of your CPU cycles. Again, because the most expensive thing that Soroban does right now is this VM instantiation. So the smaller you can make your WebAssembly files, the better. Another one would be if you're doing cross-contract calls, is what is getting a lot of people. The more cross-contract calls you're doing to unique contracts, the more VM instantiation you're going to be doing. So this number is just going to keep going up. So you might think, oh, I'll make my contracts really, take one contract and break it into 5 different contracts, and then we'll just do cross-contract calls only when it's necessary. Yeah, your singular smart contract might get smaller, but every time you do this VM instantiation, it's pretty expensive. So you have to design your contracts carefully to handle for this VM instantiation to keep this number as low as possible. because this is where most of your budget is going right now. All right, sweet. So we're using the optimized contract. I'm going to go ahead and not use the optimized contract here, and we'll do this mint. So I think we're doing 23. I've gone ahead and done all the building and mining of colors for this example that I'm demonstrating here. And we're going to call a simulation. You might wonder where all this stuff is coming from. The Soroban CLI provides this really nice bindings command, which will build out client bindings for a contract. You provided some arguments. I've got 2 of them here. One of them is for the optimized version of what I'm calling the color glyph SDK, and one for a non-optimized. So this is the non-optimized version, so I can demonstrate how at 23 width, we'll do this supermint. We'll notice this error that comes back from, let me just do my fetches. We'll notice this error coming back from the RPC where my budget has exceeded its limit. Hopefully we'll get some better errors eventually on what exactly was exceeded, but it's not able to build the simulation. So if I go to Postman really quick, and let me pull up the, I've got the RPC. Let's do a simulate transaction endpoint. So here's this. This is basically exactly what this is doing behind the scenes when I do the supermint right here. It's going to call this glyph mint. So behind the scenes, my color glyph SDK is calling this RPC endpoint for a simulate transaction. It's taking in this parameter, so we can call this right here, this same thing, and it's going to do the exact same thing that we saw there, where the budget has been exceeded. So that's not what we want the simulation endpoint to do. And this is again where I was eventually getting to the point of I need to be able to bypass simulation. So whatever simulation is going to provide me and do after that, before I actually do a send transaction, I'm going to need to be able to get by that, figure out what that is. But then if we were to use the optimized version of the contract with the exact same parameters, we're actually able to get past it, and instead of running into that error. So if I go here and do the simulation off of the same code here, we're now not going to get that error because we're using a different contract, the one that's actually optimized. And I've gone ahead and mined all those colors again. But for the same width, we get back the actual response from the simulation, which is going to provide us a good hint as to what we're probably going to want to do, and that's transaction data and costs. So what it's estimating the costs to be. And you'll notice that this is below that 40 million. And so the simulation endpoint, that's why that doesn't throw. And this transaction data is kind of the bit that we really want to take a look at, along with, I guess auth is separate here because it's also included in transaction data. But let's go ahead and take a look at this on laboratory, because this is what's going to provide us the information necessary to go and rebuild without using simulation, right? Because even though this one works, if I try and go beyond 23, right now I've figured out that I can actually do a 41 max at that 100 million CPUs. But if this ever estimates above or costs more than 40 million, right now the simulation endpoint fails because of that discrepancy bug. But if I can bypass this, I'm able to actually hit that 100 million, which can actually give me a 41 width, which is pretty incredible. But anyway, let's go ahead and look at this. One of the most enjoyable bits of Soroban development is figuring out what in the world XDR value this is. So if we go to Soroban transaction data, that's what this is. And we start to get some good information about our Soroban transaction data, being this footprint. So we can see our read-only values, reading some contract data and some contract code, and it's going to write some values, and these values being the actual mining or minting of the contract. And this all comes from my contract when things are saved to the ledger. So like owners and who the miner is, etc. We can see the instructions. And something kind of interesting here to note is the CPU instructions that it used during simulation was 38 million, and the instructions here that it's saying that it's going to try and use or budget for is 43 million, which is actually 15% more. So between simulation and submission, what's actually being set in the transaction data always increases by 15%. I don't exactly know why, but somewhere along the line that was decided, which is another reason you might want to build this transaction data XDR manually. If you don't like that it adds 15% arbitrarily. But then there's some other values here on the number of read bytes, number of write bytes, metadata, and you can read all about this in the Soroban docs, what these values actually are. But regardless, especially these values in the read and write footprint, these are going to be super important when you're actually trying to build this manually. So I like to actually use this simulation endpoint to get this transaction data so that I have some idea, and to get the auth. The auth is not included in this. So any authentication that's happening, you can use these values as hints when you go to actually try and build this manually. So hopefully that's all helpful. We'll go ahead and go to this code here. So this is the test that I wrote to try and kind of bypass the simulation endpoint and get right to a send transaction. Because a Soroban transaction isn't just an operation. So like a Stellar transaction, it's only going to be a Stellar operation, some random, whatever, payment, managed data, some offer. That's all you have to do. That's all you have to do for a simulation for Soroban. But when you actually submit a Soroban transaction, you have to include this Soroban data. And then the operation also could potentially include some authentication, additional authentication requirements. In Stellar, all you have to worry about signing is the actual transaction, not any individual authentication inside of like a smart contract. So Soroban operations include both the function, the thing you're actually calling, so the contract address, the contract function, any arguments to that function, and then also additionally any sort of additional auth that you're going to need to sign for, which is great, except for you've got your operation and the authentication. Again, that can be really helpful by decoding your auth that came back from the simulation. You can get some hint as to what it might actually need to build inside of here. So you have to build out that entry with its credentials, root invocation, et cetera, et cetera. And looking at either the simulation or actually going through the whole process of submitting, you can look back at a transaction to see what the construction of the authentication was for a successfully submitted transaction, to figure out kind of a hint at what these might need to be for any individual transaction you're trying to build manually. The real meaty bit is this Soroban data, which is all of the pieces that relate to the fee structure for actually metering out a transaction to calculate what you're going to need to spend. So this includes, again, like what we saw, where you've got the resources, footprint, the bits that you're reading, contract data, contract code, and the write bits. So it's a bit long. I mean, there's obviously things you could do to improve this. I think even since I recorded this, or wrote this code, the SDK, Soroban client SDK, has improved some of this process to be a little bit tighter. But then in my instructions, I'm just including a maximum budget, 100 million instructions, the max read bytes, the max write bytes. So this transaction is going to be absolutely the most expensive it can possibly be, but I don't really care. I just want it to get submitted because I'm trying to test my contract. I'm not trying to optimize for efficiency. I'm trying to A, get around a bug, and B, just get this thing submitted. So I'm going to max out my my budget. So that's the Soroban data. And then when I actually go to build, I put in the operation, which includes the auth and the function. And then I set that Soroban data with this resource footprint. So this is exactly what the simulation would have given me if it hadn't failed. And then I pop this all back in. Obviously, it would have given me a better estimation on my resources, but I'm just going to max that out and then submit that. So this is how I got around that 40 million issue and was able to get all the way up to a glyph that contains that 40 million or 41 that 41 width. And beyond that, I'm exceeding the 100 million CPU, where even the max budget won't pass. So that'll be my upper limit. Thankfully, I'm really probably only going to allow 16 by 16, but it was good to know how close are we to the budget, particularly when your glyph contains a maximum number of unique colors. Most glyphs will only have like 6 or 8 or 10 unique colors, but testing your max, your crazy path, is important. So anyway, hopefully that's a little bit helpful for both how to test against actual WASM code when you're looking at budgets instead of Rust code, and then also how to bypass the simulation endpoint, regardless of, hopefully we don't have bugs, but there may be times where you need to understand the simulation endpoint is not magic. It's just building a valid transaction, and it's comprised of the operation that you're submitting, and then also the Soroban data that you're submitting. I don't know, it was very helpful for me to realize these things aren't magical or hidden behind some black box in the RPC. These are things we can build ourselves client side. So anyway, I hope that's helpful, and we will catch you later.